This video lecture covers the transformation of an entity relationship model into a relational model. The primary source material for this is the textbook, chapters or sections 6.7 and also 6.8.6. And if you're using the 6th edition of the textbook, it's 7.6 and 7.8.6. The primary material we will cover in this is how to transform an ER model into a relational schema. And we will start with simple entity sets with single values, simple attributes, and then we will address more complicated scenarios. We will move on to weak entity sets, specialization and aggregation, and then something that doesn't tend to get covered in textbooks very well. We will talk about alternate approaches, and in particular alternate approaches that are based on the data mix. And I will also cover sequenced information here. So entity sets and relationship sets can be expressed as relation schemas. This is important because we do not have an entity relationship database, we have a relational database. The textbook will tell you that for each entity set and relationship set, there is either a unique schema that assigns the name of the corresponding entity set or the corresponding relationship set. To which I will say, no, there isn't. For any non-trivial entity relationship model, there are multiple possible schemas. That doesn't mean there aren't well-defined rules for doing the translation. It just means this is not a mechanical process. If it was a mechanical process, we wouldn't need to cover the topic. You would just run the thing through some translator that would automatically translate. And so do not be fooled into thinking there is some unique way of doing things. There will be design trade-offs that you will have to address and think about. Okay, in certain cases, there will be more or less unique ways of doing things, or effectively unique ways of doing things. In certain cases, total participation being a good example, the schema for the relationship set will not actually wind up having its own relational schema. It will be collapsed back into one of the entity sets. And so we'll see this showing up in particular when we address the subject of cardinality constraints. The attributes of the schema reflect the attributes of the entity set. So there is going to, broadly speaking, be a connection between the entity set attributes and the relational set attributes. However, it's not that simple. How do we translate cardinality and participation constraints? Well, we're going to wind up covering that also to some degree. Most of it will be covered within this. Okay, we'll start with the simple case, entity sets with single-valued simple attributes. And there is an identified primary key. The primary key here is the ERM primary key. Okay, do not confuse the entity relationship model primary key with the relational model primary key. They are usually the same, but occasionally there will be differences. Occasionally you won't even have a set, so completely different. So, single-valued simple attributes, meaning they're not composite, they're not multi-valued. So, if the entity set is not a weak entity set, then we simply reduce it to the relational schema with the same name and the same attributes. I am using red here again, as with the ER models, to indicate the relation name in this case rather than the entity name, and green to indicate the attribute names. The underlined attribute or attributes is the primary key. Alternatives to this, the only alternative is the attribute order could be adjusted. There may actually be reason to adjust the attribute order. Not necessarily, but occasionally you may want to adjust the attribute order. In particular, you may want the fixed length items, the fixed length items first. Okay. The system will generally take care of that for you, but for various reasons you may wish to do that. Okay, what about composite attributes? Again, we're going to keep it relatively simple. We'll talk about single-valued composite attributes. The textbook, unfortunately, when they discuss alternatives, stick to just the alternative without comparing the alternative in relation to other alternatives. So they don't tend to consider multi-valued composite attributes or things like that. So, single-valued composite attributes, all you do is flatten out the hierarchy. So first name becomes first name, middle initial becomes middle initial, last name becomes last name. You may want to generate a scheme like, name, hyphen or underscore first. For example, this, typically if you had a composite attribute, you would have name first, middle initial, last, and so you'd have name first, name last, etc. Okay, but fundamentally it is flattened out, so the structure is lost in terms of the relational model, the fact that that was a composite attribute. Okay, and same thing here. And so if it's a composite with a composite, it all gets flattened. Alternatives, naming scheme, attribute order. Okay, these are always true. I will not mention them further. What about multi-valued simple attributes? So, and just a single instance of it. So let's consider phone number. It's a single, multi-valued, simple attribute. A separate schema is required. So the separate schema will call it typically by the name of the attribute. So phone number, phone number. If there is a name clash, then that would have to be resolved. The primary key of this might be less than both attributes, but has to be could require both attributes. It depends, for example, whether or not phone number is unique to a given ID, and we will discuss that issue later. The attributes that are required as part of this are the primary key of the main relation. In this case, the main relation is instructor, and then the multi-valued attribute. The main entity no longer has the multi-valued attribute. That is omitted. So we have zip, then we have date of birth, and phone number is completely omitted. We've already covered what the primary key is, and as I said, it may be a reduction of that, but that's your worst case scenario. This ID will be foreign key to the main relation. Okay? So each phone number will have a separate entity. So let's say we have, let's say we have phone number, and we have ID and number, and you know, I need to change the background on this. This is obviously not working as a background. Maybe that works better. Okay, so person number 123 has phone number 8888888, and person number 123 also has phone number 1234567. So it will be repeated. This, as I said, is foreign key to the main relation. So we cannot add a person unless that person exists in the main relation. Okay. unless that person exists. If phone numbers are not shared, so let's say we have person number 456. If person number 456 shares the phone number, then we can see that we need, and let me change the color here, we can see that we need both numbers to identify the relation tuple uniquely. If, however, this is not possible, and every phone number that a person has must be unique, say 888-1234, then only this needs to be the primary key, okay, if unique. Okay, now I know why I used a different background color. Alternatives, we're going to discuss that when we talk about data mix options at the end, because there are definitely alternatives to this. Now, what about if we had a multi-valued attribute in a composite? Okay, if we have composites like contact method and it has a few multi-valued attributes, this person has 3 phone numbers and 2 email addresses, the best way to handle this generally would be the same as if it was a single multi-valued simple attribute. In other words, we collapse it down to the main entity. Okay, except we're not collapsing it down to the main entity because it's a multi-valued, so we're going to create an additional schema for each multi-valued attribute. Okay, so although this is a composite, we're treating it as though it was part of the main entity, but a multi-valued attribute. So over here, we have instructor, and we have contact, we have name and whatever else, and we have contact, and within there we have these multi-valued attributes. What we do instead is pretend that in fact the relationship is name, and then whatever these are, and so we're now treating them as though they're just in the main relationship and not part of a composite. And just rename the beast. Okay, so if necessary, and if not necessary, we don't rename. So it's effectively as if we have phone number in the main entity as a multi-valued and email in the main entity as a multi-valued. And so we treat them just as we did in the previous line. We have 2 separate relations, that one and that one. Okay, we do not have a contact methods with different attributes in. We don't do that. So as with any composite, we lose the composite except within the name. Again, we'll look at data mix options at the end. Foreign key, always the primary key of the main entity will be part of the primary key of the subrelation, provided that these are not unique. Email addresses tend to be unique per person, and so it would be very unlikely that this would need to be part of the primary key in a case like this. This attribute in both subentities, though, is a foreign key to the main relation. Okay. Multi-valued composite attributes. So if you remember, we had this nasty little thing where we had a multi-value address. Okay. And so a person has a couple of addresses. Okay. This is a single composite address attribute, but with multiple possible values. We handle this similarly to a single multi-valued simple attribute. Okay, so create a separate entity, address, primary key of the main entity, together with these attributes. So we would have, in the case of an instructor with multiple addresses, we would have something along the lines of instructor, and there's an ID, etc. And we would have an address table with ID and street number, street name, whatever it is. And because these are multi-valued, they all form part of the primary key. This is foreign key back to this, but collectively they all form part of the primary key. Okay. Constituent attributes of the composite address are, of course, emitted from the main entity, same as any multi-valued attribute. Again, see data mix options at the end for alternatives. And let's consider this totally messed up situation where we have mixed single value and multi-value within a composite. So in this particular case, city. Okay. And as I said, I used to live at this particular address, and it did indeed have 3 possible city names: Willowdale, North York, or Toronto. So now we're talking about a multi-valued with multiple entities. Now, in principle, the way you handle this is you create an ID, and you have a mapping here. If city was a complicated thing, this makes sense. City in general is not a complicated thing, okay? So this makes very little sense in this particular context, because we are literally creating a separate relation in order to avoid a duplication over here, when arguably the correct option is pick a city and just use it, which is what we'll talk about in data mix options at the end. Having separate entities here that allow us to say, okay, street and province are the same regardless, PKID, and then we have the city, it doesn't actually help us. And it doesn't help us because if we think about it, we've got this address that is a multi-valued address. And because it's a multi-valued address, we've got the PK of main entity, which is foreign key back to instructor. And then we've got street number, street name, city. And we'll skip the province. Only this becomes city ID. And so we have 1, 2, 3, 4001 Bayview. Okay, and city number 1. And we have to repeat this anyway, and we have to repeat this anyway for the 3 different city locations. We have no particular choice. The fact that this becomes a multi-value attribute doesn't save us from doing this. It only makes sense in the context of having a very complicated entity there. Most databases will not do this at all. They'll solve it by different means that we'll talk about at the end. Okay, relationship sets. So, let's talk about a relationship set with single value descriptive attributes or no attributes at all. So, this. Not multi-value. If its attributes are composite, the constituents are single value. So, if you think about the buys relation, if you think about the buys relation in assignment 2 that we looked at, that relation consisted of a date and a time and a quantity and a price. Those are all single valued attributes. Okay. If any attribute is composite, constituents are single valued or no descriptive attributes, as I said. This is represented as a schema with attributes. The primary keys of each participating entity set are part of it, and the attributes corresponding to the descriptive attributes the descriptive attribute are part of it. Okay, treating composites in the same way. So if we have this as an example, student ID comes from here, instructor ID comes from here, and we have date coming from here. Student ID and instructor ID are foreign key to their respective relations. So student ID will be foreign key to the student relation. Instructor ID will be foreign key to the instructor relation. The primary key in the worst case is the combination of student ID and instructor ID. It may be reduced depending on the actual cardinality within the relationship set. And we did define that previously. The primary key is essentially the primary key of the relationship set, which we may or may not need. Okay, is a relation necessary for a relationship set? All possible cardinality constraints have defined primary key for the relationship set. So, we have three relations: ID, name for instructor, ID, name for student, student ID, instructor ID, and date. Now, I've deliberately omitted primary keys. Suppose a student entity has a one-to-one cardinality constraint. So a student has to have an advisor and must have at most one advisor. In English, the student must have exactly one advisor. In that case, this relation serves no purpose whatsoever. Well, almost. There's date, except it still serves no purpose whatsoever. We achieve the same effect by having the student entity, the student relation that corresponds to the student entity set, having ID, name, and we add an attribute advisor. And in this particular case, because there is an descriptive attribute, we would have to add date, of course. And so this, that would be part of a separate relation here, is subsumed into the student relation. There is no advantage. The advisor ID is, of course, foreign key to the instructor ID, just as it would be foreign key to the instructor ID here. Okay, and this would be foreign key. There is no foreign key because there is no separate relation. Can we do this if we have a 0-1 cardinality constraint? In other words, a student may or may not have an advisor, but if the student has an advisor, they have at most one advisor. Well, if they don't have an advisor, then that's going to be null, and so that would be bad. What do we do? Well, in that case, the what do we do would be we wait and see what the options are at the end. Because at the moment I want to go through the formal rules and then we'll consider the alternatives. What if both instructor and student had one-to-one cardinality? Okay, that's a situation in which an instructor has exactly one student and a student has exactly one instructor. Okay, doesn't make much sense in the context of instructors and students, but there are examples where it would make sense. For example, you might say, every employee must mentor exactly one other employee, and every employee must be mentored by someone. So you would have a situation in which you have this mentor-mentee relationship. If both of them are one-to-one, then the relationship could be placed in either case. So when the student is one-to-one, we put it here. If the instructor was one-to-one and the student was not one-to-one, we would put it in the instructor relation. If the student or the instructor, if the student and the instructor are both one-to-one, then we could put the relationship in either of them. Again, go back to the beginning when they talked about uniqueness. Sorry, not unique. You could do it either way. Let's think about ternary relationship sets. And we're now talking about the project an instructor guides a student on a project. And this is the project guidance relationship. Students work on research projects under the guidance of an instructor. The constraints we had in that case was a student must have a project and an advisor, but may have more than one advisor. Instructors are not required to advise students or have research projects, and projects must have a designated principal investigator. In other words, a project must have a designated instructor. Okay. PI means principal investigator. That is a one-person relationship. So if there's 5 instructors associated with the project, only one is the designated PI. So this is saying a project in relation to instructor, there's this one-to-one relationship. The instructor, of course, is 0 to many. An instructor doesn't have to have any projects, but could have many projects. So, broadly speaking, here's the instructor project, which I guess I just wrote out. The student instructor, student must have an advisor, could have many. The instructor-student, instructor doesn't need to have any students, could have many students. And a student project, student must have a project, must have exactly one designated project they're working on. And projects may have no students, and I put in M here because typically there's an upper bound on the number of students associated with the project. This could be a star relationship. So what does the project guidance relationship wind up looking like? Well, it could look like this. There's an instructor ID, student ID, and a project ID. A student and a project, those would uniquely determine it. We don't need the instructor ID. Why would the student ID and project ID uniquely determine it? Because the student has exactly one project, and the project is associated with the student. The student uniquely associates with the project because the student has exactly one project. Where are we? Here. Okay. And the project, there could be multiple students. So we can't have just the student being sufficient. Okay. An alternate approach would be we could have the instructor ID and the project ID, because a project is associated with an instructor and each project ID is likely to be unique. And then separately within the student relation, we simply have this is the project you're associated with, because you're required to associate with exactly one project. Alternately, again, over here, we could have project ID, and the project has an instructor ID. And we don't even have anything in the student, and we don't even have a project guide. All 3 of these are possible. There's different trade-offs and thoughts that could go into which you would prefer. Again, these particular options are based on these particular cardinality constraints. Different cardinality constraints, and you would consider different things. Broadly speaking, this is what it would be in your worst case, with each as acting as a primary, as part of the primary key. Roles in schemas. So let's consider courses have prerequisites. What's the cardinality of these relations? Well, a course may have multiple prerequisites, and a course may act as a prerequisite for multiple other courses, but a course need not have any prerequisites, and a course may not act as a prerequisite for any other course. So typically a terminal course is prerequisite for nothing. A first-year course has no prerequisites. Okay. Both entities are many-to-many. The role relation winds up being something like that, okay, where in this particular case the role is prereq. Okay. Both course ID and prereq ID would be foreign key to the relation that they are referencing. Now, in this particular case, because it's a role schema, they are both referencing the same thing. So course ID and prerequisite ID are both foreign key to the same thing, course.course ID. Let's think about a variation of this. What if it's a married role where the entity is person? So person 1 is married to person 2. Now a person isn't required to be married, but a person is married to at most one other person. In that particular case, you have person 1 and person 2. They will both be foreign key to the person relation. Okay. But as foreign key to the person relation, only one of them would be needed because you are married to only one other person. You don't need both. What if it was a father role with the entity person? So you're identifying your father. Every person in that case, so unlike married where it's 0-1, a father relation is 1-1. You have exactly one father. At that point, the person relation would be better to simply have a father identity in it. And so if we have ID, father ID would be foreign key to the ID within itself. So that's a concept worth thinking about for a bit. We have person, there is an ID, okay, there is a, whoops, son, child of, father of, okay. So, 1-1 in here, okay. Not every person has children, and a person could have multiple children. We have name and whatever else. Father ID. This is the foreign key relation. That's worth thinking about. You can have a foreign key relation, even multiple foreign key relations, from a table to a table. Now that has implications in terms of how do you load the data. Because if you're enforcing your foreign key relations as you load your data, you will have an issue. So, point being made, there may not even be a separate relation, depending on what the nature of the relation is. Let's talk about weak entities. So we had section, and we had course. And so a section is a weak relation to a course. Has primary key, course ID, section ID, semester and year. The primary key of the strong entity, or the entity it depends on, and the discriminator. The relation schema corresponding to the weak entity section is going to be the following. Course ID, section ID, semester and year. Is there any other attribute that's not part of this? Well, in this there isn't, but one could imagine different information. Room number, time, whatever information happens to be in here that's not part of the primary key. So there might be additional information there. This, in principle, could have descriptive attributes on it, okay? But the key point is this weak entity section is in a one-to-one relationship. It has to have a course it corresponds to, and it has to have exactly one course it corresponds to. This one, there could be multiple sections. This is a 0 to star. A course could be defined and never offered. It could be offered multiple times in a semester. It could be offered in multiple years. Okay. So, what does this mean? Well, unless there's these attributes here, and even if there are, okay, unless they're multi-valued, even if there are single value attributes here, there is no need to have a relation for sec course, okay? That is not necessary. It is subsumed into the section relation formed from the section entity. Unless there are multi-valued attributes here, if they're just single-valued attributes or none at all, any attributes will also be subsumed into there. Further, the primary key of the entity course is already in the section relation, so no additional attribute is required there for the section relation. It's already in there. Okay? And of course, this is foreign key. Don't forget that. Specialization. Okay, so let's think about overlapping generalization. A person could be an employee, could be a student, could be an employee and a student. And depending whether it's total or partial, a person might just be a person. If it's partial generalization, partial specialization instead of total, a person could be a person and be neither an employee nor a student. Okay. For example, a visiting researcher. Okay. If we do a top-down approach, we start by defining a person relation. ID, name, address. We then define schemas for the lower level entities in which we use the primary key of the higher level entity and then whatever the specific attributes are of the lower level entity, where these are foreign key back to this. So ID is foreign key from student to person, ID is foreign key from ID to employee. If I want to access information specific to employees or specific to students, I'm going to have to do a join. So select whatever from person in a join employee using ID to do the join operation. Okay. If I want to, I can create a view employees, and notice I use a slightly darker red here because it's a view. It looks like a relation, it looks like a table, but it's not. Okay, so I create a view and the view is whatever that is. So this is an employee's view and it simply is joined there. This, by the way, not necessarily a good idea, but I'm using it just for illustrative purposes. Generally, spelling out exactly what it is you want in your view is better. What if we do bottom up? Okay, bottom up, we define, in this particular case, we have disjoint generalization. Okay, ID and rank, and ID and hours per week. Again, ID of these will be foreign key to the employer ID. Okay, that would be the top-down approach. If we take the bottom-up approach, we say, okay, an instructor has an ID, a rank, and a salary, an ID, and hours per week, and a salary for a secretary. ID is not a foreign key here. Okay, ID is ID. You can't do the bottom-up approach here, or you probably shouldn't, with overlapping generalization because you would have an ID here and an ID here, possibly for both of them. Okay, so you could get duplication and that can get messy. To access information general to employees, you need to create a union of the two. Select ID salary from instructor, union ID salary from secretary, and that will give you the general information, and the general information, of course, is only salary. What happens if the generalization is overlapping or partial? Well, you have a horrible situation. For example, what if, let's go over to here. What if we have an employee number 123 and a student also 123, and what were the, instructor and, right, no, we want to imagine it's a overlapping, so employee and student. So in this particular case, an employee, I believe, had salary information as well as other stuff, and a student had credit information. Okay. Go back here. Student has credits, employees have salaries. Okay. So, student has credits, 4.3. Salaries, 23,000. Not a problem to join those in principle at that level, but if we're doing bottom up, they'll also have address info. So we'll have to have an address here. Now, what if the address here and the address here, what if those are different? We've got a problem. We've got a big problem. Because we're doing a union over the IDs, and we'll have two different addresses. So we're going to have 123 address 1 and 123 address 2. We don't know which is the address. So bottom up shouldn't be used for overlapping generalization. Bottom up shouldn't be mixed with top down in a single hierarchy. And in general, I would advise avoiding bottom up unless there's a very good reason to use it. And I cannot, in general, come up with any scenario in which there is a good reason to use it. Notice also, I can have partial information here. So let's think about this for a moment. Suppose you had optional attributes. A person has a name and an address. Now, what if they had some optional attributes like hair color and middle name? In that particular case, you can actually imagine this as a partial generalization scenario. And this is a person, and it's an overlapping partial generalization. Person with middle name, person with hair color, etc. Now, I'm not going to argue that this is a good solution, okay? I would argue that this is a terrible solution, but it is the only solution that the entity relationship model has for optional attributes. You create separate entities for optional attributes. I would argue that the moment you have overlapping generalization, you probably have a bad scenario to some degree. Not necessarily. But in particular, if you have partial generalization or partial specialization, however you want to word it, as opposed to total, the type of thing that works well for is if you have things like there's employees and the students, and you're starting out your university, and so there's some people who aren't employees or they aren't students, and they're visiting researchers. And so in the initial instance, you didn't have this. So you may have a partial generalization, and you can model that as top-down, and you have employees, you have students, and if you have a lot of people falling into a category that is optional, so they're not here at this point. They're only in this top level at this point. You don't have the category visiting researcher. Then as the number of people who are at this level but not at a lower level, as that number grows, you modify your ER model to introduce an additional entity to capture that group of people, or that group of whatever the subdivision is in the specialization. It isn't really a good method for dealing with optionals, okay? But we'll talk about that later. So we've covered this. Again, if you do bottom-up, you can create a view, employee as, okay? There is, by the way, a big problem with this. You can't do a foreign key to that. You can't maintain foreign key relations. This is a problem. So, drawbacks with the bottom-up approach. I said I dislike it, so I'll talk about specific reasons. If specialization is total, then the generalized entity set contains no information. In other words, it contains no... let me rephrase that. If I have a total generalization, whether it's disjoint or not, doesn't matter. If this is total, then there is no entity here. There's no person here. There's no whatever. Nothing here that isn't here. Okay? And so if we're doing bottom-up, the information is all here, and this is a view on top of that. There's no additionals. If it's partial, then I would need support for that. So let's say I had instructor and I had secretary, but I had someone who's an employee only. I'm going to have to create a separate relation for an employee only thing. Okay? And I would need to subsume them in that. Okay? Second, overlapping generalization is not necessarily disjoint. Okay, key point here. What do I mean by not necessarily disjoint? Just because an employee can be a student doesn't mean most employees are students. In fact, most employees are not students. One could actually, that's not true because there's TAs, but let's ignore TAs for now. One can readily imagine that although an employee could be a student, there are no employees who are student. So it's not necessarily disjoint. The particular data may be disjoint, but if it is not disjoint, if there is an overlap, then I'm going to have redundant information, and I already talked about that. You could have an employee and a student at bottom up in which you have two different addresses, and so you've got inconsistency. That, by the way, that represents even a legal problem. For example, suppose a university department keeps track of your address, and the library keeps track of your address, and the registrar's office keeps track of your address. The university, as a legal entity, is a single legal entity. As long as you've informed one of them of your new address, you have informed the university as a legal entity of your new address, unless the university has an explicit statement to the contrary. So this inconsistency may even have legal implications. Okay? Worse, it's possible to create a view that provides for the general entity. The view can never be updated. Why? Because it's based on a union. Some views can be updated. A view based on a union cannot be updated, and it cannot be updated because you don't know which underlying entity you're updating. If you update the salary information here in the view, does it go into the instructor table, the secretary table, or the employee-only table? The database has no way of knowing because there is no unique way of determining that, it cannot do it. So you cannot update the view. The second problem, it cannot act as a reference to foreign keys. For example, if there's benefits available to employees, the benefit has an ID. The ID wants to be foreign key to the employee ID, but there is no employee ID table. If you have materialized views, you may be able to enable that. Okay. So you might be able to get around this problem with a materialized view if you've got one of the big three databases or possibly Postgres. Postgres has materialized views, but they're not automatically refreshed. It doesn't address this problem. Okay, aggregation. If you recall, we had this notion of an evaluation for project guidance, which was done with an aggregated entity. The schema for the aggregation is the schema for the relationship set of the aggregation. So literally, we treat this as though it's the same as any relation, and we've already talked about how to deal with relations. Broadly speaking, it's going to look something like this if there's no relevant cardinality constraints to simplify it. So we'd have the primary key of the evaluation ID and the primary keys of each of these, which is in fact the primary key for project guide. So these are not coming because they're primary keys for instructor, student, and project. These are coming because they are collectively the primary key for project guide. Okay. For precisely this reason, it may well be useful to create an identifier for project guide to simplify the schema. So one thing that is useful in normalization, required no, useful yes, is if you have a complicated primary key like this in a relation, it's probably useful to create a project guide ID that uniquely identifies a project guide, that does a mapping between project guide and these entities. I'll leave you to think about that. Let's talk about alternate approaches, and the textbook doesn't particularly address this. But based on data mix, likely usage, and in some cases our willingness to tolerate nulls in the design, there's a whole lot of alternatives. So let's talk about options for single multi-valued simple attributes. So phone number. We've got several options. Option number 1, give me a number. I don't care whether it's your home number, your cell number, your wife's mistress's dog's number. It really doesn't matter. Just give me a phone number, because all I want is a phone number. It is a contact method for you. If you give me a contact method that's useless to reach you, well, then sucks to be you if I need to reach you. Okay? This is a very, very standard solution. Okay? Very common. A classic example is the whole middle initial. Okay? If you think about people with multiple middle names, what does the standard database do? It says, give me a middle initial. You've got 3 middle names, pick one. We don't care. Okay. Option number 2. We could define different types of the attribute. So it's very common that when we have something like phone numbers, we don't really have multiple phone numbers. We have multiple types of phone. We have your home phone number, your cell phone number, your office phone number. In fact, some databases will talk about your daytime and your evening and weekend. Okay. So if I'm calling you during normal office hours, I would expect to call you on your office phone. This is implicitly an office phone versus a home phone. Okay. An emergency contact number. Now, if we define different types of phone, we actually increase the probability that one or more of these attributes simply doesn't exist. So, for example, you may have a cell phone and not have a home phone. You may not have an office phone. Okay. The typical solution to this is not to use nulls. Why not? Let's say you only have a cell phone. So you're asked what your home phone number is. Give them your cell phone. And your cell phone number? Repeat it. And your office phone number? Repeat your cell phone again. And your emergency contact number? Okay, that's mum or dad or spouse or whatever. That should be different. But these, if you only have one, you typically list them 3 times. Okay, so there may be different types. Okay, same thing for address. You may have multiple addresses, but instead of dealing with it as a multi-valued variable for address, you say, okay, what is your permanent home? What is your home while you were a student on campus? Okay. And then a third technique, and this is also a common one, is to have preferences. So what is your preferred phone number? What is your alternate phone number? School boards will do this typically. Suppose you have a child in school, they will want a list of contact numbers to call in sequence. So who's the first contact to call, but maybe you can't get through to them, in which case you call the second contact. If you can't get through to them, you call the third contact, etc. This is a common technique, and in fact, if you think about it, an emergency phone number is effectively a form of alternate phone number. Okay. So I've already given examples, but again, middle initial, that's common. Okay. Now, data mix matters. If most people have only one phone number, then a good solution is, instead of defining all of these, what you do is you define the person as having a phone number, and then you have a separate table of additional phone numbers. So instead of having everything in a separate table, and this is particularly true if you have any constraint of the form 1:*. So let's say a student is required to have an advisor, but may have more than one advisor. Well, if they're required to have an advisor, we have student ID. We can't put advisor ID here because they could have more than one. But what if we've got 1,000 students and 3 of them have an alternate advisor, a second advisor, and one of the 3 has a third advisor? It would be silly to have a relation advisor with ID and advisor ID, because every time we wanted to look up the advisor, we would have to join with this table. This table would be as big as the student table, which means we'd have as many IDs here as we have here. So a waste of space. The join operation is more expensive because this is a bigger table. And everybody has one advisor anyway. If we simply have additional advisor, then we put an advisor ID here. Now, if our objective is to find, and this, by the way, would help if we could describe that as the primary advisor, if we can break it down the way we do here with the idea of a preferred phone number, okay, where you have an additional, that helps. Okay, but even if we don't have that, this is probably the way to go for this type of relation in which everybody has one and very few people have a second. So there'll be like 3 entries here, number 456 and number 627 and number 931. These are the only people who have it, which means even if whenever we're looking for the advisors, we need to find all advisors, we've only got to join this 3-person table. This will be super fast. Whereas if we have 30,000 students and we have to join to find every advisor with a 30,000 table, it's much more expensive. So when we have this data mix in which has very few additionals, and there is this required, then placing the required one in with the main entity and having a separate table just for the additionals is probably much to be preferred. Okay. The having a phone number attribute in instructor, same type of thing. Having an additional instructor phone. Okay. What about other composites? So, if we have contact methods, unless there's a compelling reason to the contrary, cases like this are best treated as if the composite doesn't exist and simply treat the multi-valued attributes in the main entity. We've already discussed that. Multi-valued composite attributes, so we have multiple addresses, require a single specific address. Much, much simpler. Problem solved. Don't need to mess about with these different cities. Just give me one address. Give me one thing that is where you are going to receive your email, or mail, where you're going to receive your parcel, whatever. Again, if you really care about it, define different types of addresses. So universities, for example, will have the home address and the campus address. Okay. And define different preferences for address. This is where we're going to try and reach you if we need to reach you, but if we can't, give me a second alternative. In particular, suppose you talk about cottages, as people might have multiple addresses. Well, the vast majority of people don't have a cottage. So again, having that alternate address as a separate table rather than having all addresses in a separate table would be the better way to do it. The mixture, in this case, pick a city, okay? Makes no sense, okay? If you really have to do the alternate approach, have alternate city, ID and city. That solves that issue. 0, 1, and 1 cardinal, 0 to n and 1 to n cardinality. Okay. It's often the case that although the rules imply a particular cardinality constraint, the practical situation differs. So we've already talked about this. A student is required to have an advisor but could have more than one. The implied constraint is 1 to star. The practical constraint is the vast majority are 1 to 1. So doing it this way, student has an advisor in their main relation. This is the primary advisor. If we only want one advisor, this is the one we're going to contact. And these are the alternate advisors. And if there is only one alternate advisor allowed, if it's a 1 to 2, then only one of these attributes would need to be primary key. Okay. If a student isn't required to have an advisor, but could have more than one. So we've got whoops, I got this backwards. We've got a 0 to star relation. Again, what is the data mix? Do most students have an advisor? If most students have an advisor at some point, we might go with this solution and accept the fact that it's null to start with. Okay, not necessarily great, but it's a kind of okay. The alternate is to have a default advisor. So, for example, in electrical and computer engineering, the associate chair for graduate studies is the default advisor if the student's advisor disappears. For example, suppose your advisor gets run over by a bus. Or your advisor leaves the university because they move somewhere else, and they're no longer in a position to supervise. And we require students to have an advisor. We have the default advisor is the associate chair for grad studies. So this doesn't even necessarily need to be null. It can be default as the associate chair graduate studies in this particular case. So we can have a default. Okay. With apologies over the fact that the MySQL system doesn't handle setting defaults on constraints very well for foreign keys, but separate discussion. Okay, if many students do not have an advisor, then a separate relation would be best. Okay, so for example, if you have an employer situation and some employees have mentors, but most employees don't have mentors, then you probably wouldn't want to have a mentor attribute within your employee relation. You would just have a separate table for that. So that, broadly speaking, deals with that issue. Let's think about middle names. Okay, and there's a reason I'm going to talk about middle names, because many people on the planet don't have middle names, but there's a reason why this is applicable. Broadly speaking, before I talk about it, the reason it's applicable is what we're really talking about here is sequenced information. And so recording the moves in a game or sequence of instructions, this is really significant. Any sequenced data. So let's talk about middle names as an example of sequenced data. Some people have a middle name, some people don't. Some people have multiple middle names. Standard approach in North America, what is your defined middle name? For those without a middle name, this should be used. Not null, but because null says we don't know what your middle name is. We don't have information. Whereas this, the empty string, if you will, \0 as a character, okay, is the middle name is nothing. Okay. Now, this tends to be reasonable because most people in North America have a middle name, or most people used to have a middle name. What the status is now, I don't know. But the problem with this is, let's take these requirements seriously. It's often the case that people think of middle names as a multi-valued attribute, but that's not right, because they're sequenced. You have a first middle name, a second middle name, a third middle name. So to pick a particularly famous individual, Charles Philip Arthur George Mountbatten Windsor, aka Prince Charles, has 3 middle names. But they're in sequence. It's Philip Arthur George. Okay. So how do we deal with this? Option 1, already discussed. Pick one. Okay. Option 2, place them all in a single attribute. Okay. You can, but that doesn't really work because you've lost, you haven't lost the sequencing information, you've lost the ability for the database to process it as sequenced information. Okay, this one is lost extra names. Okay, this is lost ability to process in DB. And that's important, okay? For example, if you say, what's the third middle name? Okay, that would be kind of dumb. What if you were talking about moves in a chess game? How many times in a chess game is the knight moved before the 5th turn? Okay, that's something that you can't possibly do here. Okay. You could create multiple attributes and use nulls for those without the full complement. So we have a person and we have middle name 1, middle name 2, middle name 3. You could use nulls or you could use double quote. Double quote would be better. Okay, this one is not great. This one is not great because most people don't have 3 middle names. And so if you don't have 3 middle names, you've got a problem. Like if most people have 1 middle name, these are empty for most of them. Okay, not necessarily good. Okay. Conversely, what if a person had a 4th middle name? You've still lost the information. So this is probably just a basically bad idea. There are circumstances in which it's an okay idea. For example, if you know exactly how many things you have, it can be useful. So let's think about Yelp data. Or for that matter, if you think about timetabling data in a university context, you have certain opening hours, hours when it's open. Well, this is Monday, Tuesday, Wednesday, each day of the week. And then you've got midnight to 1 and 1 to 2, etc. Okay, so you got 24 options here and you got 7 options here. You've got a fixed number of options, and so there are cases where you may want to create a set of rules if you know what the fixed set is. Okay, we could create a middle name relation where we have ID, name, and number. ID is foreign key to instructor ID or whatever it is, person ID, whatever. Problem with this. Okay, I have a 47th middle name, but I don't have middle names 1 through 46. There's no constraint on this. There's no ability to say you can't have a second middle name until you have a first middle name. So you can do a variation on that, which is creating a separate relation for each possible middle name. So, middle name number 1, ID and the name. This ID is foreign key to instructor ID. Middle name number 2, this ID is foreign key to this. In order to have a second middle name, you must have a first middle name. In order to have a third middle name, you must have a second middle name. Now this is really good if you're talking about sequences of moves in a game or sequence of instructions where you have a reasonable upper bound on the number of instructions or moves. You could augment this with this if you have a data mix such that 95% of cases are less than, let's say we're talking chess games. 95% of chess games have 40 or less moves. And then you say we'll augment moves beyond 40 with a separate thing. So if we talk about moves in a game, move 1, move 2, etc., up to, say, move 40, and then you have move beyond 40. Okay. And this is foreign key to this, which is foreign key, which is foreign key, which is foreign key, etc. So you would have this to capture anything that's beyond 40 moves or whatever your upper bound is. But the way you would be handling it is the vast majority, preferably all, are captured within these relations. Okay. Every option has its limitations. Some are worse than others. This is probably your best option unless you have what is called a heavy tail distribution. Let's suppose you're talking about Lego instructions. I have kids, so I know about Lego instructions. Actually, the kid that likes Lego the most is over 20 at this point. Some really cool car games. A lot of Lego instructions are like 30 or less. But then you've got big models that are like 900 or more instructions. Now, if it's like this, you got a lot of cases here that still need lots and lots of instructions sequenced. So broadly speaking, all I can say is ordering data in a relational database is not well supported. But that's that, and that's broadly the different alternatives. Hopefully this helps you transform entity relationship models into relational models. And we will then continue future lectures talking about so-called normalization, or more precisely, detailed database design.